All right. So here's what we've talked about up to this point. Up to this point, we were looking at relationships between different factors of gas particles, and we were looking at the scientific laws that describe them. It was Boyle's law, Charles' law, and Gay-Lussac's law. Okay. And all three of them related two of these factors here, while the third one was kept constant. We talked about two different ways of describing it. One is we could describe it qualitatively. That was where we were describing what was happening with the particles. That's when I mentioned the kindergartners. Okay, changing things like the size of the room that they're in, the amount of energy they have, the number of times they collide. But we also talked about them quantitatively, where we actually calculated what the temperature, pressure, or volume would be if we changed one of the other variables. The expectation here is that you're able to do both. Okay, I want the particle explanation, but I also want you to be able to accurately predict, well, what exactly will the pressure be if I increase the temperature by this amount? Okay. One of the things with this is when we did the calculations, I told you that the problem you were doing was a Boyle's law problem. So you use P1 V1 equals P2 V2. Okay, because you had written down the formula, all you had to do was plug in the numbers. Same thing with Charles' law. I told you that the three practice problems were that law, and so you didn't have to do a lot of thinking about what formula to use. You just had to kind of copy it down from your notes. Now, on the test, it's not going to be like that. It's going to give you a problem, but you're going to have to decide which one of these it is. Okay, you're going to have to evaluate, okay, what variables are being manipulated, which variables being held constant, and that's going to help you decide which one of these three gas laws you're going to have to use. So I want to give you an example of kind of the process of working through that. So let's look at an example together. This is a good chart to reference. Okay, this chart is a little bit bigger. There's one more box down here that we're going to talk about in a second, but I have it on its own slide so that you can reference it when you're taking the test. But remember, the things that we're looking for when we're trying to decide which one of the laws it is what variables are being compared and what variable is being held constant. Those are the hints that are going to allow you to determine which one of the gas laws it is. It won't be on the test, but it's its own chart on its own slide with no other words. It's just this chart, so that it's really easy to find if you come looking for it. But yeah, I'm not going to put it on the test. If you want to use it, you'll have to come find it. All right, let's look at this example and try to figure out which one of these laws it would be. It says a compressible container at constant pressure has 14 liters of hydrogen gas at 25 degrees Celsius. During the day, the container increases to 35 degrees Celsius. What's the volume of the gas now? So let's think about what's constant. It tells us that it's a constant pressure. If you can figure out the constant, that's pretty much all you have to do. Okay. The constant here is pressure. Pressure is held constant, so it has to be Charles' law. Let's double check that this problem is comparing volume and temperature. It says volume 14, temperature 25. What changes is the temperature, and we're looking at now how volume is going to respond. It is definitely comparing how temperature and volume are related, while pressure is being held constant. So that tells me that this is a Charles' law problem. So when I go to do these calculations, you first have to make sure that you select the right one, and then now you can use the formula to actually do the calculation. Do you have questions on this? This is why it's important to be doing these problems. Okay, it's a little bit more than just using the formula. You also have to recognize when it's appropriate to use each one by really thinking about what does that law describe? What two things are being compared and what's that one thing that's held constant? I don't know if it was in this class or another class, but someone asked me, well, what if more than one of the variables is changed? Okay, let's say we do something to a gas and the pressure and the volume go up, or the pressure and the temperature go up. What effect would that have on volume? Honestly, in the real world, okay, it's pretty typical to have more than one variable change. It's actually pretty hard to keep one of them constant. Okay, obviously in controlled environments, it's a lot easier, but out in nature, there's usually more than one variable changing. So what I want us to do is I want us to look at, well, how do we predict if two variables change, what's going to happen to that third one? We can make these predictions. It's just we can't use the formulas before, okay? Because the formulas that we've looked at in the past depend on one of the factors always staying the same. In this case, we're going to have two variables that are changing, and then that third variable is going to respond in some way as well. So they end up all changing. And so what we have to do is we have to come up with a different formula. It should look really familiar to you. Okay, it's called the combined gas law. If you look at this formula and you look at the name of it, really what it is if you look at Boyle's law, Charles' law, and Gay-Lussac's law, and you put them all together, you get the combined gas law. Now, in Boyle's law, look at its formula here and compare it to the combined gas law formula. It's missing one of the parts, right? It's missing temperature. It's missing temperature because temperature is held constant. In Charles' law, compare it to this. What part is it missing? It's missing the pressure part. Why? Because in Charles' law, pressure is held constant. And then in Gay-Lussac's law, volume is missing. Why? Because volume is held constant. So that's the relationship between these. Is the combined gas law, all of the variables are in there because all of the variables are changing in some way. They were either changed at the start or they change at the end as a result of that relationship. So when do we use this? We're going to use this formula here anytime there's more than one variable that's changing. Okay, if they're all changing over the course of the event, then we have to use the combined gas law formula. Which means you're probably going to be given 5 pieces of information and you're going to be missing one of the variables. The process of solving these problems are the exact same. You have to read the problem to figure out, okay, well, what was the starting pressure, volume, and temperature? What was the final pressure, volume, and temperature? And making sure that you pull out the right pieces of information and get them put into the formula correctly. It's not super difficult, but if you've never seen one of the problems before and you try to attempt it on the test, it's probably going to look like a foreign language to you because you're going to have no context on what exactly it's asking. I want to go through a practice problem of solving one of these with you. Andrew, here's that slide that I was talking about. It has Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law all in here for you. Here are the descriptions reminding you of the things that are held constant. Now remember, on the test, it's going to be more than just, what's held constant in Boyle's law. Okay, anyone can Google that. Okay, it's going to be more process of, I'm going to be asking a lot of prediction questions. Like, if I do this to the pressure, can you predict what the volume will do? what gas law, supports that description or describes why that relationship exists. And then that's when you would mention something like Boyle's law or Charles' law. So this is a good slide to have for the test. You're more than welcome to make a snip of this or copy it, or just make sure you know it's in here. All right, here's one of those combined gas law problems. If you would please work this out with me as we go through it together. A balloon is filled 2.5 liters of helium gas at 98 kilopascals and 24 degrees Celsius. 24 degrees Celsius, okay, we don't use Celsius, remember. So we're going to end up converting that to Kelvin. The balloon is released into the air and floats up into the sky. As it climbs, the pressure changes to 61 kilopascals and the temperature becomes 5 degrees Celsius. What is the volume of the balloon now? So the reason why this is a combined gas law problem is because during the event, okay, in the middle of the before and after, the thing that changed was both the pressure and the temperature. Since there is more than one variable that has changed, we need to use the combined gas law formula. I did this out on paper, okay, and did the various steps. So I'm going to have that come up now. So combined gas law formula, that's where I started. P1 V1 over T1 equals P2 times V2 over T2. The first thing I did, so I did not forget to do it, was I went and looked at my temperatures here and I converted to Kelvin. Remember, when we're talking about gas laws, we're really focusing on particle motion. And so we are going to use the temperature scale that stops at 0. That's Kelvin. The conversion factor from Celsius to Kelvin, very simple. You just take the degrees Celsius, which is 24, add 273, and then you end up with your Kelvin temperature. So for my second one, I did 5 plus 273, and that gave me 278. So now I have my initial and my final temperature. Now I need to look at where this other information goes. So it started out at 2.5 liters. So that goes here. That's my starting volume. Kilopascals is pressure. So my starting pressure is 98. That goes here. I need to put that over the initial temperature. We crossed out this 24 and I changed it to 297 Kelvin. So that goes on the bottom. Set that equal to my new pressure. It looks like the pressure went down to 61 as it climbed in altitude. Multiply that by the new volume, which we don't know. Okay, that's what it's asking us to find. What's the volume now? And then our final temperature was 278. I got that by taking the degrees Celsius and adding 273 to it. Once we get all of the variables in the right spot, then we need to make sure that we do the algebra right. Okay, solving this is very similar to the Charles or Guy-Lussac's law, where we're going to have to cross multiply, and then we're going to set those products equal to each other. So be careful on this. Okay, there are several different ways to work this out. This is my preferred method of doing it. If you have some other way of doing it and you get it right, that's completely fine with me. Okay, but here's how I suggest doing it. First, I'm going to cross multiply here. So it's going to be 98 times 2.5 times 278. That's what I have on the left-hand side. Set that equal to the product of the other crosses, which is 297 times 61 times V2. That's here. Once you've cross-multiplied, then it becomes a little bit easier to isolate your variable, V2. All you need to do is divide away the 297 and the 61. Divide that on both sides. And then here's kind of the setup before I even put it in the calculator. Now, please, please, please make sure you're being careful when you put this into the calculator. It kills me when you've done all of this work right, and then you get to this step, and you accidentally push the wrong button, and you get the wrong answer. And then you think you've done everything wrong, which you didn't. It was just you hit the wrong button. Here's what I would do. I would do 98 times 2.5 times 278, hit enter, and either write down the number that goes on top, or keep that number in my calculator, hit divide, and then make sure I put the bottom in brackets. So I'd do bracket 297 times 61, close it off with another bracket, and then hit enter. This gave me an answer of 3.75 something something something, but I rounded it to 0.76. These problems should look familiar to you. Okay, the only thing that we've done differently is we've added in a third variable. The challenge is figuring out the ones that changed and then getting them in the right spot here. One thing that I've seen people do is I've had a couple people start to mix up like what liters and what kilopascals actually mean. Liters references the volume. Kilopascal references pressure. Celsius or Kelvin is temperature. So if you're having problem recognizing those, go back to when we talked about volume and pressure and look at some of the different units that we've been using. I think that will help with this identifying step. What questions do you have for me? While I'm waiting for questions, your homework for tonight is the mixed gas law calculations. So what I've done is I have given you some of the old gas law problems, but this time I did not tell you which one of the gas laws it is. So the first thing I ask you to do is tell me what gas law it is. And then the second part is do the calculation and give me the number. I've also mixed in a couple of the combined gas law calculations. So you have 4 different options. It could be Boyle's law, Charles' law, Guy-Lussac's law, or the combined gas law. Because really the first step in doing these calculations accurately is knowing which gas law it is and using the right formula.